So I'm looking at this learning target, and it's talking about still using the properties of exponents, but we're getting into zero and negative exponents now. So I want you to think about zero and negative exponents. I want to show you why kind of they work the way they do, and the answer isn't always what you thought it was going to be. So first, 2 to the fourth power we know is 2 times itself times itself again, which is 16. 2 to the third power is then 8, which means 2 squared is 4, and 2 to the first power is 2. We know those. Those are numbers we've worked with a lot. These, with the zero exponent and the negative exponents, we really haven't worked with. So let's think about what's happening here. Every time I move down 1, my exponent goes down 1, I could get this answer to this answer by dividing by 2. And that'll work all the way down here. Which means to move from 2 to the first power to 2 to the 0 power, I'm going to divide by 2 again. So 2 to the 0 power is 2 divided by 2, which is 1. It's not 0, which you might want to say it is. If you put any number except for 0 itself into your calculator and raise it to the 0 power, you're always going to get an answer of 1, if you do it correctly. Don't forget, if it's a negative number, like negative 512 raised to the 0 power, negative numbers raised to exponents have to be inside parentheses. So negative 512 to the 0 power is 1. Positive 1 billion to the 0 power is 1. 2/3 in parentheses raised to the 0 power is 1. So it's always going to work that way. Another reason it works that way is you saw in the notes yesterday that if you take something like y squared and divide it by y squared, well, we know that something divided by itself is 1. You've known that forever. 6 divided by 6 is 1. 12 divided by 12 is 1. Negative 3 divided by negative 3 is 1. So you know that this is 1, because something divided by itself is 1. But using the rules of exponents you learned yesterday, if I divide two things with the same base, I subtract the exponent. So this is the same thing as y to the 2 minus 2 power, which is y to the 0 power. So something raised to the 0 power is the same thing as taking something and dividing it by itself, and you get 1. That's also why if you try to take 0 to the 0 power, it's going to give you an error, because the way it calculates that is it knows raising something to the 0 power is like dividing something by itself. You can't divide by 0, therefore you cannot take 0 to the 0 power. Keeping this going, if I keep dividing by 2 all the way down, what I end up with is 1 divided by 2 is 1/2. 1/2 divided by 2 is 1/4, and 1/4 divided by 2 is 1/8. Notice that 2 to the positive 3 power is 8. 2 to the negative 3 power is 1 over 8. So that's the same thing as 1 over 2 to the positive 3 power. Also notice that this negative exponent did not lead to the number itself being negative. Negative exponents are all about the reciprocal of the first number, not about the number itself being negative. And then a number raised to the 0 power equals 1. So, looking at the problems, the first thing I'm going to check is to see, like here, I have two different a's. I'm going to combine them in a minute. I have three different m's. I'm going to combine them in a minute. But I only have a single x, a single y, and a single z. So this is simply a division problem to begin with. 4 divided by negative 2 is negative 2. So I could put this as 2 over negative 1, but 2 divided by negative 1 is still just negative 2. The way I taught this in class was, it's not a good math phrasing, but if you think of exponents like being little thought bubbles above a cartoon character's head, whether they're thinking negative thoughts or positive thoughts. So the x is thinking negative thoughts. It's not happy. Its thoughts are negative. The only way you can make the x happy is to move it. So it moves from the numerator to the denominator, and then its thoughts are happy. The y has an exponent of positive 1 already. It's happy staying where it is, so the y stays put. The z has an exponent of positive 4. It's happy, so it stays where it was. Alphabetically, x comes before z, so x to the third should come before z to the fourth. And then here's the challenge that you have to remember. People want to move the negative 2 because they say the negative means it's unhappy and it wants to move. But the exponent, the thought bubble above that negative 2's head, is a positive 1. So its thoughts are positive, it stays put. When I see this division problem, it's a lot like the division problem in part 2 of the notes. First, I'm going to reduce this fraction. 14 over 20 reduces to 7 over 10. And then, when I divide things with the same base, I subtract the exponents. So a to the 4 minus 6 power, which is 7a to the negative 2 over 10. I cannot have a final answer with negative exponents. The exponent on the 7 is positive 1. It's happy. It stays put. The exponent on the 10 is positive 1. It's happy. It stays put. But the exponent on the a is negative 2. It's not happy. It's thinking negative thoughts. It needs to move to become a to the positive 2 in the denominator. Now, negative 4 over negative 6 reduces to a positive 2/3. I have m in 3 different places. I need to get down to a single m. If these are all m's, any exponents in the numerator get added. So 4 plus negative 2. Any exponents in the denominator get subtracted using the rules that we already learned in the last couple of days. So I end up with 2m to the negative 6 over 3. But then I'm not allowed to have negative exponents, so the 2 stays because positive exponent. The 3 stays. Exponent is positive 1. The m moves so that the exponent can become positive. Now, if this had been like this instead, we're going to do example C1. If, let's say, we don't even have to reduce this, if it was 2/3 already, if it was m to the 4th over m to the 12th, m to the negative 3rd instead, I would try to reduce this fraction, which in this case I can't. I take my 4, I subtract these exponents in the denominator because I'm dividing by m to the 12th and I'm also dividing by m to the negative 3. So 4 minus 12, minus negative 3 would be 2m to the, this would be negative 8 plus 3 is negative 5th over 3. And then I don't want that negative exponent, so 2 over 3m to the positive 5 would have been my answer. In this case, as soon as I see negative exponents outside of the parentheses, I do everything I can to simplify what's inside before I worry about that exponent. I notice this s to the fourth divided by another s to the 4th. That's just 1, so those are going to cancel. 6 over 12 reduces to 1 over 2, and then I have an r to the negative 3 minus 4 power. Because if I'm dividing things with the same base, I subtract the exponents. And then I still have this negative 2 exponent out there. So I end up with r to the negative 7th over 2, and then this whole thing is raised to the negative 2 power. When I raise a power to another power, I multiply the exponents, which we did in in part 2 of the notes. So r to the negative 7 times negative 2 over 2 to the negative 2 power, because the exponent here was 1 to begin with. That gives me r to the 14th over 2 to the negative 2. I can't have a negative exponent though, and I can't square the 2 if it's being raised to a negative 2 power. So the 2 moves to the numerator, where the exponent becomes positive. My r stays put because the exponent's already positive, and this would be over 1, but we're not going to write the over 1 in the final answer. So I end up with 4r to the 14th power by the time I'm done.